All right, here we go. So our next unit is going to be about vectors. So in this video, we're basically just going to learn the basics. Here's your learning targets. Make sure you read through them. I think they're fairly straightforward. So here we go. So first of all, a quick review. You need to make sure you understand the basics of right triangles. I tend to find that honors students don't have any problems with this. So I guess really two things. So first of all, you got to know the Pythagorean theorem, that anytime you've got a right triangle, that the sides of the two legs, if you square those lengths and add them up, that gives you the same thing as the length of the hypotenuse squared. Remember, the hypotenuse is the side across from the right angle, and it is always the longest side of the triangle. All right? And then you should know your SOHCAHTOA, right? That once you pick your angle, there's an opposite side, and an adjacent side, and a hypotenuse. And sine, cosine, and tangent are functions on angles. So if you take the sine of that angle, it's equal to the ratio of the length of the opposite side divided by the length of the hypotenuse. So h. The ka is cosine of the angle is the length of the adjacent side divided by the hypotenuse. And TOA is tangent of theta is the length of the opposite over the length of the adjacent. I think you all know that. So if you have questions or don't know what any of this means, please make sure you come talk to me so we can get you up to speed on it. All right, so some definitions. First of all, a vector. All right, we talked about this already in the last chapter very briefly, but a vector is a number that's got both magnitude and direction, whereas a scalar is a number which has just magnitude. All right. I feel like I never stress this word magnitude enough. The magnitude is basically just the number part of a number, okay? So most of the numbers that you've dealt with in your life are scalars, like how many slices of pizza did you have? 3. So the magnitude of the amount of pizza you had is 3 slices, all right? So a lot of numbers in science are, in fact, scalars. Time is a scalar. Distance is a scalar, right? How far did you drive? 40 miles, okay? How fast are you going? 30 miles an hour. Okay, a vector is a number that has both magnitude and direction, all right? And just having a different direction makes it numerically different, all right? A position of positive 5 miles is different than a position of negative 5 miles. Having a displacement of 30 meters is different than a displacement of negative 30 meters. Or 40 miles north is different than 40 miles, west. All right, velocity, your direction is important. Acceleration, your direction is important. Force, which we talked about briefly, the direction is important. Pushing a table to the right is different than pushing a table to the left. Okay, so some values that we talk about are vectors. Some values that we talk about are scalars. Technically speaking, anytime you write a vector or a quantity that it's a vector, you should put a little arrow over it. So like really, velocity ought to be v with a line over it. That's called a vector hat, okay? So in displacement, really I should be writing displacement, okay, and putting a little arrow over it like that to indicate that it is a vector. Force ought to be F, acceleration ought to be like that, all right? But it just gets tedious writing those all the time, and except in very specific instances, it's not usually that big of a deal, all right? So when you do this, when you write, now I'm getting ahead of myself. All right, anyway, so there you go. Now you know that. Okay, so one-dimensional vectors. So everything we dealt with last chapter was one-dimensional vectors, right? Remember, we indicate the direction just by using positives and negatives, all right? So examples, if Esther walks east 2 miles, then, the displacement of Esther is 2 miles, and we could either write east or just call it positive. And the displacement for Wally, because he's going west, is negative 2 miles. All right, and we can pictorially represent these with arrows, and this is going to be important. So here's the displacement for Esther, and here's the displacement for Wally. Okay, notice they're both the same length, but they point in opposite directions. All right, if we had somebody who went 4 miles east, then we would draw it twice as long. Okay, so the length of the arrow represents the magnitude of the vector. Okay, so let's see. In the next example, we've got a ball being thrown up into the air, so the initial velocity is positive 30 meters a second. and the final velocity is negative 30 meters a second. You gotta make the little sounds, all right? Let's see, a car driving forward speeds up at 2.5 meters a second squared. So the idea is the velocity is this way, and because it's speeding up, that means that the velocity is going to get longer in this direction. So the acceleration points in the direction that the velocity is going because the acceleration is working with the velocity. So here, the acceleration of the car is positive 2.5 meters a second squared. And the acceleration of the truck is driving forward but slowing down. So the acceleration of the truck is working against its velocity, and so it points to the left, okay? Alrighty, so that's that. Please notice that this displacement is different from this displacement because they have different signs in different directions. Similarly, these two velocities are different, and these two accelerations are different. All right? All right, now, two-dimensional vectors. In the real world, not everything happens on a number line, so we need to learn how to deal with this. All right? In two dimensions, so it's funny because in one dimension, there's only two possible directions you can go, right? Like if you've got a number line, you can either go this way or you can go that way, right? But in two dimensions, there's an infinite number of directions you can go. So you can go that way, or 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 that way. You get the idea, right? There's an infinite number of directions you can go. So just using a positive or negative doesn't tell us enough, okay? It doesn't tell us what direction we're moving, all right? So we need to find another way to describe the direction, and the way that we do that is by using an angle and a little bit of description, too. All right, so in this first example, it says a car drives 300 kilometers at 40 degrees south of west. So what does that mean? Well, I'll draw a little compass. Let's see, north, south, east, west. So let's see, here's west, but we want south of it. So I want to go 10, 20, 30, 40 degrees south of west. So there's the 40 degrees, and then displacement is, 300 kilometers? Okay. But notice here, the 40 degrees is measuring how far off of west I am, in this case, south of west. North of west, if it had been north of west, that would have been up here. Okay? All right, in the example below it, we've got a jet that's flying 400 miles an hour at 60 degrees east of south. So this time it's a velocity vector, but we can still describe the direction similarly. This time it's 60 degrees east of south. So here's east, here's south. So we want to go 60 degrees east of south. So here's south, here's 10, 20, 30, 40, 50, 60 degrees east of south. West of south, well, so let me write this out. So my velocity is, what did I just say, 400 miles per hour at 60 degrees east of south, okay? West of south would have been, here's south, and then 10, 20, 30, 40, 50, 60 degrees over here. So this would have been west of south, all right? All right, so usually, though, our directions are not going to take place sort of on a compass. It'll just be about throwing a ball. And so basically, you can throw a ball up, which we'll describe as above the horizontal, or down, which we'll describe as below the horizontal. So here, he's throwing it at 32 meters a second at 20 degrees above the horizontal. So the idea is, here's horizontal, and he's going to throw it at 10, 20 degrees above the horizontal. 32 meters a second equals V. Okay. All right, and in this last one, Carl pulls a rope that makes an angle of 50 degrees with a vertical wall using a force of 500 newtons. So I know you guys don't know exactly what newtons are, but you can still understand this, right? Because we've got, here's our wall, our vertical wall. Here's the rope. It makes a 50-degree angle with the vertical wall. So 10, 20, 30, 40, 50 degrees with the vertical. That's a terrible 50 degrees. And here's the force of Carl, 600 newtons. Okay? So notice when you do it this way, you don't use any negatives because making, for example, some of you might be thinking, well, the force is, oh, I guess this one doesn't really tell you what direction it was, if he was pulling up or down. That one's worded badly. All right, anyway, making this negative wouldn't tell you anything, right? Like, would that negative mean left, or would it mean down, or what? Okay, so you really need to make sure you describe it. Okay, and like I say, this description is not enough. Okay, because there's no way of knowing if he's pulling up at 50 degrees or down at 50 degrees. Okay, but anyway, so this is how we describe the direction of a two-dimensional vector. All right, now, unfortunately, you can't type 60 degrees east of south into a calculator. All right, so to do that, we need to find a way to deal with these vectors in a calculator. All right, and to do that, we deal with what are called the vector components. All right, so the horizontal component is a representation of the vector's magnitude, but just in the horizontal direction. The vertical component of the vector is a representation of the magnitude, but it ignores the horizontal portion and just focuses on the vertical. All right. Note, the two components are one-dimensional, all right? So we can use positive and negative. All right, so my guess is I plowed through this, and you're probably like, what is he talking about? This is really easiest to explain by using an example. So let's dive in and do that, all right? So suppose we've got a car that's driving, as we said, at 40 miles an hour at 60 degrees east of south. Let's find the horizontal and vertical velocities, all right? So here is the deal. Let's make our little compass again. So here's east, here's south. So we said 60 degrees east of south. So 10, 20, 30, 40, 50, 60 degrees east of south. So here is my vector. So my velocity is 40 miles per hour at 60 degrees east of south. All right. So what I want to do is I want to make this into a right triangle, which includes the angle. Okay. So let's see. If I draw a vertical line here, that'll represent my Vy. It's the vertical velocity. Okay. So the idea is, as the car is driving south, it's making progress, or as the car is driving, it's making progress south. So this Vy will be a representation of how quickly the car is moving south and ignoring any motion east or west. Similarly, we can close off the triangle and find our horizontal component, which we'll call Vx, and that'll measure how quickly the car is moving horizontally. Ignore the vertical motion. All right. I was going to say a thing, and I lost it. Oh, I know what it was. Okay, cool. Sorry. So notice the horizontal component will always be, so in this problem, our vector had it was called v for velocity. Okay. The horizontal component is Vx because the x-axis runs horizontal. So the horizontal component of any vector will have the same name, subscript x. That's always the horizontal component. And then the vertical component will have that same name, but a y, because of the vertical axis. So because the vertical axis runs vertically, just like the y-axis. Okay? All right, and so from this point, it's now just a little bit of SOHCAHTOA to figure out what your missing component is. So here, my Vx is my, opposite side, right? Vx is the opposite side, and I know my hypotenuse, so I think I can use sine. So I think that the sine of 60 degrees ought to be my opposite over my hypotenuse. Okay? And then, so that means that Vx is just going to be 40 times the sine of 60 degrees. Make sure your calculator is in degrees, not radians, and find out what your Vx is. And it gives you 34.6 miles per hour. So that is a representation of how quickly the car is moving east. All right. Similarly, I had to be able to find my Vy. Vy is the adjacent side, so instead of using sine, I'm going to use cosine. So the oh shoot, I wanted to change colors. So the cosine of 60 degrees ought to equal my adjacent side over my hypotenuse. So Vy is going to be 40 times the cosine of 60, which gives us 40 cosine 60, 20. Oh, obviously, miles per hour. Okay, so what's happening then is my car, for every hour that it drives, it's going to go 20 miles south and 34.6 miles east. Okay, now remember, these are now one-dimensional vectors. My Vy can, going to lie along the y-axis or parallel with the y-axis. So it can either go up or down. Here, my overall motion was south, therefore my y component points south, so this is negative. Okay? For my x component, the overall motion was southeast, so the x component points east. East is positive, so this is a positive Vx. Okay? So our ultimate goals here were to find our Vx, or sorry, our Vy and our Vx. Okay? All right. Sometimes we got to go let me pause here. A couple things. So first of all, these two vectors, Vx and Vy, are called components. They will always be drawn head to tail. In other words, head of one vector touches the tail end of the other vector. Okay? And the resultant vector, the overall vector, the hypotenuse vector, will always be head-to-head with one of the components and tail-to-tail with the other component. Okay? Notice the directions of the two components model the direction of the overall vector, right? Here, this vector points south and east, so my two components have to point south and east. Okay? All right, so sometimes we got to go the other way. Oh, that's funny. I said exactly what it says there. All right, so what if a plane's velocity has horizontal component of negative 300 miles an hour and a vertical component of 400 miles an hour? Let's find the overall velocity. All right, so we're going to draw the two components. Here's what we know. We know that the horizontal component is negative, so we know that that's west. And we know that the vertical component is positive, so that's north. So I know that my overall vector's got to point north and west. So I have to draw my two components. So now, which component you draw first doesn't really matter. All right, I usually draw the x component first. So here we go. So we're going to go west. Here's the velocity horizontally. It's negative 300 miles per hour. All right, and then I want my overall vector to point north and west, so I got to go up here, right? So here's my Vy, positive 400 miles per hour. Notice head to tail for the two components, and then the overall vector points in the direction that the two vectors suggest. In other words, we want to go west and north, and this is going northwest. Okay? So, to figure this out, we're just going to use the Pythagorean theorem, right? So, if this is Vx and Vy, then this side is V. So, Pythagorean theorem tells us that V squared ought to equal Vx squared plus Vy squared, right? So 300 squared plus 400 squared is V squared. So solve it, and your V turns out to be 500 miles per hour. All right, now we need to describe the direction. So I need to use a little bit of trig and find this angle here, theta. All right, so to me it looks like theta is going to be the inverse tangent of opposite over adjacent, 400 over 300. And you don't need to worry about your negatives there because you need an angle between 0 and 90. So inverse tangent of that gives you 53 degrees. So my velocity then is, what do we say, 500 miles per hour at 53 degrees. And what are we doing here? Let's see, this is west, and we are north of it. All right, so there you go. All right, finally, occasionally I'll give you something like this, where you got to kind of piece things together. So it says a force is directed at 20 degrees south of west, or south of east, so draw it. So let's see, here's east, we want 20 degrees south of it, 10, 20. So here's my force. The vertical component is 50 newtons. It's got to be negative, right? Otherwise this wouldn't make sense. Here's the 20 degrees. Here's my vertical component, negative 50 newtons, right? Because south is negative. So we got to find the magnitude of the force and the horizontal component, right? So it's really just a little bit of trig, right? You've got your triangle, okay? You know the opposite side and the angle, so you got to find your other two sides. All right, so if you do that, then you get, I chose to use tangent to find my fx because I knew my opposite and my angle, and I was trying to find the adjacent. Oops, I forgot my units. And I used sine to find my f. Really, I could have used Pythagorean or cosine at that point, but I wanted to make sure that I used a number that wasn't rounded, so I used sine. All right, so there you go. That's it.